A siren blares inside a Soviet command bunker. Above, something is moving faster than a missile, Mach 3, 80,000 feet, and accelerating. Foxbat pilots scramble, convinced their MiG-25s can bring down the intruder. By the time they reach the edge of heaven, the Blackbird is already gone. These are the true events behind every failed interception, a contest that would rewrite what both superpowers believed about speed, technology, and the future of war. What did it take to build an aircraft no one could catch? The answer begins decades earlier in a race driven by Cold War fear. On May 1st, 1960, a U-2 spy plane flown by Francis Gary Powers was shot down over Soviet territory. The wreckage was paraded in Moscow, and the pilot became a bargaining chip on the world stage. That single missile strike shattered American confidence in the skies. In Washington, the CIA faced a crisis that cut deeper than any public embarrassment. The president demanded answers. How could the United States peer behind the Iron Curtain now, with every established method suddenly exposed and vulnerable? Inside the CIA reconnaissance board, the mood turned from shock to urgency. The language in their classified directives was blunt. No more risks with slow, high-flying aircraft. The Soviets had proven their missiles could reach any intruder. Intelligence gaps widened by the day. Satellite technology was still unreliable, and the stakes, nuclear arsenals, missile deployments, hidden airfields, were too high to leave to guesswork. The agency could not afford another public disaster, nor could it accept blindness along the Soviet frontier. Every option was scrutinized. Balloons, subsonic drones, even new orbital cameras. Nothing promised the coverage, speed, or survivability needed. The CIA's requirements hardened. Any new aircraft must fly faster and higher than any missile could reach. It must cross hostile borders, gather photographic and electronic intelligence, and escape before a single Soviet fighter could close the gap. The board's minutes from mid-1960 captured the sense of desperation. The next reconnaissance platform had to be untouchable, or the United States would lose its eyes in the most dangerous standoff in history. Within weeks, the call went out to America's most secretive design teams. Lockheed Skunk Works, led by Clarence Kelly Johnson, received a contract under the codename Oxcart. The challenge was clear: build an aircraft that could fly at the edge of space at speeds never before attempted, using materials and engines that did not yet exist. The project's urgency was matched only by its secrecy. One internal memo stated that the survival of the nation's intelligence capability depends on a solution the enemy cannot reach, predict, or destroy. This was not a contest of ambition or prestige. It was a race against time, driven by the knowledge that the next intelligence failure could mean the loss of strategic advantage, or worse. The CIA's directive shaped every decision that followed. The sky would have to be conquered by speed, not by stealth or luck, and across the world, Soviet planners took notice, setting their own engineers to work on a counter that could match whatever the Americans dared to build. Kelly Johnson's design team at Lockheed faced a challenge that pushed the limits of materials science and aerodynamics. The CIA's requirements were uncompromising. The aircraft must survive speeds above Mach 3 and altitudes above 80,000 feet, not for minutes, but for hours. At those speeds, friction with the thin upper atmosphere would raise the skin temperature beyond 800 degrees Fahrenheit, hot enough to soften or melt conventional aluminum. Johnson's answer was radical: build the airframe almost entirely from titanium, a metal strong enough to hold its shape at extreme heat, but notoriously difficult to work with. 92% of the SR-71 structure became titanium, sourced from across the globe, even from the Soviet Union itself through covert channels. The Blackbird's skin would expand and contract by several inches as temperatures soared and dropped. Panels were engineered with gaps and special fasteners to accommodate this movement. On the ground, the aircraft leaked fuel from its seams by design, because only at speed and heat would the joints seal tight. The fuel itself, a special compound called JP7, doubled as a coolant. Before combustion, it was routed through heat exchangers embedded in the wings and fuselage, absorbing thermal energy and carrying it to the engines. This system kept the aircraft's vital electronics and hydraulic fluids within operational limits, even as the outside burned white hot. At the heart of the Blackbird were two Pratt & Whitney J58 engines, each capable of producing over 32,000 pounds of thrust. Unlike any previous jet, the J58 was designed to operate as a hybrid, part turbojet and part ramjet. At lower speeds, it functioned as a conventional afterburning turbojet. But above Mach 2.5, the engine's unique inlet spikes, long sharp cones at the nose of each nacelle, began to move automatically, retracting up to 26 inches to regulate the shock waves forming at supersonic speeds. This adjustment slowed incoming air to subsonic speeds before it reached the compressor, preventing catastrophic surges. The inlet system, guided by sensors and computers, managed airflow so precisely that at cruise, nearly 60% of the engine's thrust came from the compression of air in the inlets, not from the engine core itself. The J58 could run at maximum power for hours, a feat no other jet engine could match. During missions, the Blackbird routinely consumed more than 3,000 gallons of JP7 per hour. To maximize range, aerial refueling was built into every sortie profile, often minutes after takeoff. The aircraft's performance baseline, Mach 3.2 at 85,000 feet, became more than a number. It was a guarantee of survivability. Soviet interceptors and missiles simply could not reach an aircraft flying that high and that fast for so long. Johnson's own words, in a 1964 memo, summed up the design philosophy. The enemy can't hit what he can't catch. Every detail of the SR-71 blueprint reflected that principle. It was not just a spy plane, but a machine built to exist where no other could, beyond the reach of adversaries, above the limits of known engineering. Soviet engineers at the Mikoyan-Gurevich Bureau faced a dilemma. The Americans had chosen titanium for the Blackbird, but the USSR metallurgical industry could not support mass production of titanium airframes. Instead, the MiG-25 was built mainly from nickel-steel alloys, strong and easier to shape, but far heavier and less resistant to heat. The Foxbat's designers compensated by focusing on brute force. Two Tumansky R-15 turbojets, each pumping out 40,000 pounds of thrust with afterburner, lifted the aircraft almost straight up after takeoff. In training films and flight manuals, the climb rate, nearly 50,000 feet per minute, was a source of national pride. Soviet doctrine called for the interceptor to launch on command, accelerate past Mach 2.5, and streak toward the stratosphere before an intruder could escape. But this speed-first philosophy came with hidden costs. The airframe could only withstand its maximum velocity, Mach 2.83, for a few minutes at a time. Beyond that, the steel skin began to deform, and the R-15 engines faced catastrophic overheating. Pilots kept a wary eye on temperature gauges, knowing that a few seconds too long at full throttle could mean a compressor stall or even a fire. After any high-speed sortie, ground crews inspected the turbines for warping or cracks. The MiG-25 was a speed machine and a sprinter, not a long-distance runner. Radar was the next pillar. The Smerch, a system, one of the most powerful ever fitted to a fighter, could spot targets at over 50 miles. Its massive antenna filled the Foxbat's nose, and its electronics were built to withstand nuclear blast effects. On paper, this radar could guide R-40 missiles to a target at extreme range. In practice, the system struggled with fast, high-flying intruders. The radar refresh rate lagged behind the closure speeds involved, especially when the target was moving at Mach 3, like the American Blackbird. Soviet controllers sometimes mistook the SR-71 radar return for a missile, because nothing else moved that quickly at such altitude. The Foxbat's strengths and weaknesses became starkly clear in 1976 when Lieutenant Viktor Belenko defected to Japan in his MiG-25. Western engineers, allowed unprecedented access, found the engines lined with steel and not advanced alloys. The turbines could survive brief dashes at top speed, but not sustained flight. The cockpit was filled with analog gauges, many dedicated to monitoring engine temperatures and fuel flow. Belenko later described the intercept process as a tense, narrow window. Pilots had to reach the right altitude at the right moment, with engines screaming and the fuel tanks draining fast. Any delay or miscalculation, and the target would vanish beyond reach. To the Soviet command, the Foxbat looked like the answer on paper, faster than any bomber, able to climb above most fighters, and armed with missiles built to kill at distance. But beneath the surface, the design was a compromise, sacrificing endurance, agility, and even structural integrity for the briefest shot at a fleeting target. Every intercept order was a gamble against physics and time, with pilots pushing their machines to the edge, hoping that raw speed would be enough. A Soviet radar screen in the early 1970s was a study in patience and uncertainty. The air defense network stretched from the Baltic to the Pacific, its operators trained to scan for intruders that might appear as faint echoes in a sea of static. On a routine shift, a blip would register moving at impossible speed, high above the reach of most aircraft. The Smerch and P-14 radars, operating in the L-band and the S-band, updated their displays once or twice every second. At that rate, a target flying over 2,000 miles per hour at 80,000 feet could leap nearly a kilometer between sweeps. Each time the phosphor refreshed, the blip had jumped far ahead, sometimes vanishing off the edge of the scope before anyone could act. Doppler complicated matters. A target at Mach 3 produced a frequency shift so extreme that the radar's processors struggled to keep up. Soviet technicians had built their systems to track bombers and missiles, not an airplane that blurred the line between the two. When a Blackbird appeared, its signature was so sharp and fleeting that operators sometimes mistook it for the boost phase of a ballistic missile. The command post would buzz with confusion. Was this a warhead racing toward Moscow, or an American spy collecting photographs? The difference was crucial, but the hardware could not always tell. Pulse repetition frequency, known as PRF, set the tempo. At 1 to 2 Hz, there was a built-in lag, a heartbeat's delay between the real world and the radar picture. In that gap, a Mach 3 aircraft could be gone before the intercept geometry was even calculated. Controllers struggled to hand off targets to tracking radars, which required precise angles and timing. If the Blackbird changed course or accelerated, the tracking radar would lose coherence, the blip would stutter or disappear, and the intercept solution would evaporate. Operators watched as targets seemed to blink out of existence, only to reappear dozens of miles away, already beyond reach. Inside the bunker, the urgency was palpable. Every detection triggered a scramble order, but the technical reality was sobering. The radar's slow refresh and the sheer speed of the intruder meant that by the time the MiG-25s were airborne, the target's position was already outdated. Controllers had to guess, extrapolating from a handful of data points, hoping the Foxbat could climb fast enough to intersect a path that was more prediction than fact. The radar officer's voice, clipped and tense, relayed vectors that were already stale. In the background, senior commanders debated whether they were chasing an airplane or a phantom. This was the first fault in the Soviet defense. The system designed to protect the homeland could not reliably distinguish, track, or anticipate the movements of an aircraft that outpaced its own information flow. The Blackbird's advantage began not with speed alone, but with the gaps it created in the very screens meant to stop it. The scramble order lands like a hammer. MiG-25 crews rush from the ready room, boots pounding metal grates, helmets clutched tight. The Foxbat's ladder slams against the fuselage. Within seconds, the cockpit canopy locks shut around the pilot, sealing him inside a world of dials and warning lights. As ground crew pull chocks and signal the all clear, the Tumansky R-15 engines roar to life, their afterburners flooding the dawn with sheets of flame. The Foxbat leaps down the runway, nose lifting, wheels tucking away as the pilot shoves the throttle past detent. The aircraft surges upward, climbing almost vertically, speed and altitude building together. Every instrument is a potential threat. Engine temperature, turbine RPM, fuel flow, each one a reminder that the Foxbat is flying close to its own destruction. At 40,000 feet, the stress is already mounting. The pilot's gloved hand hovers over the temperature gauge, eyes flicking between the red line and the altimeter. Above 50,000 feet, the air thins, the climb rate slows, and the R-15 engines begin to protest. Cockpit air grows stifling, sweat pooling under the pressure suit. The Foxbat's steel skin radiates heat, and the airframe groans as expansion strains the rivets. The checklist is simple but absolute. Exceed Mach 2.83 for more than a few minutes, and the engines risk a catastrophic meltdown. The margin for error is measured in seconds. Radio chatter crackles in the headset. Ground control vectors the aircraft toward the projected intercept point, their voices clipped and insistent. The radar scope glows with target data, but the blip is already shifting, too fast, too high. The pilot pulls harder on the stick, the altimeter unwinding past 60,000 feet. The Foxbat's nose shudders, the controls grow sluggish. At 68,000 feet, the aircraft is at the operational ceiling, engines screaming, temperature alarms flickering. The pilot's breathing is shallow, forced through the oxygen mask, every muscle tensed against the cockpit's rising heat. Anecdotes from MiG-25 crews, later confirmed in technical debriefs, describe engines so hot after a maximum climb that ground crews measured turbine blades warped, sometimes blue from heat. One pilot recounted the sensation of the aircraft melting around him, the cockpit haze thick with the smell of scorched insulation. The R-15 engines, designed for brute force, could only sustain this punishment for moments. Any longer, and the fire warning lights would flash, signaling the onset of a true emergency, a compressor stall, a flameout, or worse, an engine fire at 70,000 feet. The workload is relentless. The pilot must balance engine temperature against climb rate, fuel burn against intercept geometry. There is no time to dwell on the odds. Every second counts. The cockpit is a crucible, sweat, heat, vibration, and the constant knowledge that the target is moving even faster, even higher. As the Foxbat claws for altitude, the pilot listens to the rising whine of the turbines, feeling the edge of what the machine and the man can endure. The radar officer's voice is a distant echo, the intercept solution already slipping away as the Blackbird vanishes into the stratosphere. SR-71 mission logs from the 1970s and the 1980s read like a catalogue of near misses and unanswered threats. In the Barents Sea, one entry records a radar warning at 82,000 feet, followed by a coded alert: missile launch, maintain course. The crew did not break formation or alter speed. Their orders were clear: trust in the aircraft, trust in the numbers. The Blackbird's velocity, over 2,100 miles per hour, meant that even as a missile left its rail, the distance between hunter and hunted was already growing. Colonel Darrell Cobb described a sortie off Vladivostok where his RSO calmly announced that they had a fighter locked on, probably a MiG-25. Seconds later, the RSO reported a missile launch and a lock. The Blackbird's defensive electronics, known as DEF, switched to jamming mode. Cobb's logbook for that day is matter of fact. The missile lost lock, the threat faded, and the Blackbird continued its run. The crew's heart rates barely changed. For them, the procedure had become routine. If a missile warning sounded, they accelerated. If the DEF system chirped, they trusted it would do its job. In every case, the result was the same. The Foxbat missile never got close. Pilot Richard Graham recalled looking down from 80,000 feet and seeing 3 MiG-25 jets climbing hard, their contrails arcing through the thin air. The Foxbats reached 62,000 feet, straining to close the gap, but Graham's Blackbird simply pulled away. Graham recorded that all 3 went right by underneath him, no problem at all. The visual encounter was brief, but the meaning was unmistakable. Even when the Soviets could see their target, altitude and speed kept it out of reach. Swedish air defense reports from the Baltic tell a similar story. Their radar logs recorded a recurring geometry, the Blackbird at 72,000 feet and the Foxbat trailing at 62,000, always 1.9 nautical miles behind, never closing the distance. The Swedes judged some of these events to be simulated shoot-downs, rehearsed to salvage pride or satisfy doctrine, but the real outcome was never in doubt. Declassified records from both sides confirmed the pattern. The MiG-25 jets would scramble, climb, and if lucky, get within missile range for a fleeting moment. By then, the SR-71 was often already gone, sometimes 80 miles ahead, sometimes simply vanished from radar. The tail chase was a mathematical impossibility. The Blackbird's cruise speed outpaced the missiles, the altitude gap was unbridgeable, and radar lock slipped away as quickly as it appeared. Soviet controllers logged each attempt, each failure, and each return to base with fuel tanks nearly empty and engines pushed to the edge. Across every logged encounter, the evidence is the same. No SR-71 was ever brought down. The documents do not show triumph or even hope, only a steady record of missed shots, broken locks, and the dawning realization that the Blackbird could not be caught. The logs, the pilot voices, and the technical data all converge on one fact: the Blackbird was untouchable. At 80,000 feet, the SR-71 occupied a domain that no interceptor could reliably reach. The altitude mattered. The MiG-25, even in its lightest configuration, struggled to crest 68,000 feet with a full missile load. That 12,000-foot gulf was not just a number on a chart, it was a hard physical barrier, a vertical wall that separated the hunter from its prey. Soviet climb profiles show the Foxbat racing upward at nearly 50,000 feet per minute after takeoff, but that rate plummeted as the air thinned. Above 60,000 feet, the climb slowed to a crawl, every additional 1,000 feet wrung from engines pushed to their limits. Pilots reported the last 5,000 feet taking as long as the first 50,000, with turbine temperatures edging toward danger and the altimeter's advance slowing to a tick. Even if a MiG-25 reached its ceiling, the horizontal chase was futile. The speed difference was decisive. The SR-71's cruise speed at altitude, around 2,200 miles per hour, outpaced the Foxbat by more than 300 miles per hour. A Foxbat at maximum dash, Mach 2.8, could only hold that speed for a few minutes before risking engine failure. The Blackbird, by contrast, could sustain Mach 3.2 for hours. In a tail chase scenario, the separation between the two aircraft grew relentlessly. For every minute the Foxbat spent at its limits, the Blackbird pulled ahead by over 5 miles. Charts from both US and Soviet sources quantify the gap. At 80,000 feet, the SR-71 moves faster, climbs higher, and leaves the interceptor behind before a missile can even be launched. Closing the distance was not a matter of skill or courage, but of physics. The time required for the Foxbat to climb into firing range exceeded the time it took the Blackbird to cross the sector entirely. By the time the Foxbat reached its peak, the SR-71 was already 80 or 100 miles away, invisible to radar, untouchable by missile, and accelerating further into the stratosphere. The math was merciless, and it played out the same way in every encounter. Altitude and speed combined to create a separation that no Soviet pilot could overcome. When the MiG-25 finally reached a firing position, the next barrier was invisible but absolute. The Foxbat's R-40 missiles relied on semi-active radar homing, which required the launch aircraft's radar to keep a continuous lock on the target until impact. At the speeds and distances involved, this became a technical trap. The SR-71, accelerating at over Mach 3, could cross the missile's engagement envelope in seconds. The missile seeker had a limited field of view and needed the Blackbird to remain illuminated by the radar beam long enough for guidance signals to steer it in. In practice, the closure rate was so high that the radar could not maintain a lock for more than a fleeting moment. The missile's electronics would often lose track and default to search mode as the target slipped out of the guidance window. The problem grew worse when the SR-71's defensive systems activated. The defensive suite could jam the Foxbat's radar, but even without electronic interference, the Blackbird's sheer speed broke the missile's lock. Pilots described watching the guidance indicator flicker, then drop away as the SR-71 accelerated beyond the seeker's ability to track. In some cases, the Blackbird crew dumped fuel, a tactic that cooled the aircraft's skin and altered its infrared signature just as the missile's heat seeker attempted to acquire. That sudden signature change, combined with the speed differential, left the R-40's infrared seeker hunting for a target that was already out of range. Missile logs and debriefs from both sides confirmed the pattern. The R-40, with its massive warhead and long range, was designed for slower, lower targets. Against the Blackbird, its guidance window collapsed almost instantly. The combination of extreme closure rate, brief illumination, and a shifting infrared profile made a successful intercept effectively impossible. Each launch ended the same way: seeker confusion, broken lock, and a missile drifting harmlessly through empty sky. On Soviet radar screens, the track of the Blackbird always ended the same way: a sudden gap, a blip that leapt forward and faded, leaving only a trace of where it had been. Controllers watched as the Foxbat icon crawled upward, closing the distance for a moment, but never enough. The numbers told the story: the SR-71 at 80,000 feet and Mach 3.2, the MiG-25 struggling below at 68,000 feet, redlining its engines. Even at their closest, the separation stretched to 80 or 100 miles in minutes, a distance that grew with every second the Blackbird accelerated. The radar refresh cycle could not keep up, and each sweep revealed the Blackbird had already moved far ahead, sometimes vanishing from the screen entirely. For the MiG-25 pilot, the climb ended in frustration. He reached his ceiling, gasping through the oxygen mask, scanning the empty sky above. The target was already gone, beyond missile range, beyond hope. In the bunker, silence replaced the alarms. The intercept geometry had collapsed into a blank patch on the display, and the only record left was a line of numbers and a fading echo on the screen. In 1979, a directive circulated among Soviet Air Defense Forces leadership, its language stripped of optimism. The document referenced recent intercept attempts, each ending with the same outcome. The target, identified as an American reconnaissance aircraft, had already crossed out of range by the time MiG-25s reached altitude. The memo's summary was unambiguous. The probability of successful interception was assessed as near zero. There was no mention of pilot error or technical malfunction, only a blunt recognition of physics and timing. The directive instructed sector commanders to revise engagement protocols. Priority shifted away from scrambling Foxbats for high-altitude chases, and instead focus turned to surface-to-air missile batteries. The text outlined a new chain of response. Upon detection of a Mach 3 target above 80,000 feet, tracking data would be passed directly to surface-to-air missile crews. Interceptor sorties were to be reserved for lower, slower threats. The internal tone was resigned, not defiant. In the margin, a handwritten note underscored the new reality. Foxbat intercepts against this class of target were not feasible. For the first time in official policy, the pursuit of the Blackbird was acknowledged as a mathematical impossibility. The Soviet air defense network, built for interception, was now ordered to stand down when the world's fastest aircraft appeared on their screens. Across the Atlantic, analysts at Langley reviewed the same data pouring in from Soviet air defense sectors. The CIA's national intelligence estimates from the late 1970s laid out the American view in plain language. Charts, intercept timelines, and radar plots all pointed to a single conclusion: the MiG-25 could not catch the Blackbird. The most telling phrase appeared in a classified national intelligence estimate: tail chase engagement against the SR-71 is infeasible under operational conditions. The numbers were absolute. By the time a Foxbat reached its best firing altitude, the SR-71 was already accelerating out of reach, opening the separation with every passing second. Soviet radar refresh rates, missile speeds, and climb profiles were dissected line by line. The CIA's technical branch highlighted that even the most optimistic intercept geometry required timing so precise it bordered on the theoretical. The SR-71's cruise speed outstripped the Foxbat's maximum dash, and the Blackbird's altitude advantage was beyond the reach of Soviet missiles. In closed-door briefings, CIA officers described the MiG-25 as a credible threat to slower reconnaissance aircraft, but against the Blackbird, the Foxbat was operationally irrelevant. For American planners, this was not just a technical victory, but a strategic assurance. The nation's eyes would remain open, and its adversary's best interceptor could do nothing about it. Even now, no operational aircraft has matched the SR-71's speed or altitude. Its legacy endures in a world where surveillance shifts from roaring engines to silent satellites and digital eyes. Supremacy in the skies is fleeting, but the race for information never ends. Every new breakthrough, whether stealth, hypersonics, or AI, echoes this lesson. Intelligence, not just technology, decides who stays ahead. The chase continues, measured in shadows and seconds. What do you think the next frontier will demand?